Finishing Green's theorem first. Area of the ellipse. Last time, we proved that. Since it's circulation, closed loop, 0 to 2 pi. X, A cosine of theta, dy, B cosine theta d theta, minus y is b sine of theta, and dy, I'm sorry, dx, negative a sine theta d theta. Once everything's simplified, should be a half the integral 0 to 2 pi of AB d theta. AB times pi, right? Or if we put it in the known form pi AB. There's the area of the ellipse. We're going to evaluate the circulation. Y minus sine of x dx plus cosine of x dy along the triangle that is shown. Well, before, there should be 3 separate path numbers, right? But here's 3 here. That's the region that this path encloses. describe it. X would go 0 to pi over 2, right? Y would go from 0 to whatever that line is. It's the equation of that line.
Radical is equal to d squared. A is equal to d squared. Size of the triangle, the opposite of the hypotenuse.
You can use Pythagorean theorem. A would be what? And so let's say base and height, because that's what essentially we're going to be doing here. What's the base? Length of the base. Pi over 2. What's the length? What's the length of the height?
1.
So then you can use your Pythagorean theorem there. That might be a little more difficult. Than just looking at slope-intercept form of a line. What's the intercept of this line?
Zero.
Yeah, y equals 0 is the y-intercept. Oh, that's perfect, okay. Now you just need the slope. What's the slope? What is it? How'd you get it? Slopes 2 over pi, rise over run. And slope-intercept form is what? Y equals mx plus b. Two over pi x. We also need partial with respect to x of the y component. Partial with respect to y of the x component. Right, then Green's theorem says that circulation is the double integral over d partial with respect to x of the y component minus partial with respect to y of the x component, dA. Go ahead and factor out that negative. X goes 0 to pi over 2, y goes 0 to over pi x. Sine of x plus 1 dy dx. Can just integrate with respect to y right away. We're going to get 2 over pi x. Oof, oof, oof. Now, the second integral is not hard. And that's just x squared over 2. 0 pi over 2. That first integral, though, it's going to require integration by parts, isn't it? Let's actually do this one by hand. Let's review integration by parts. What do you need when you're doing integration by parts? What is it? Technically, it's not V that you use. Oh, and dV. Okay, I didn't hear the V part. Yeah, U and dV. What's U? And dV is just what's left. And then the formula says what? What was it? And since this is an integral, not an antiderivative, we evaluate from 0 to pi over 2. That's that first term. And the second term is easy. Leave that alone. Plus sine of x, right? x squared over 2. That whole thing is evaluated from 0 to pi over 2. What is cosine of pi over 2? Cosine pi over 2 is 0. Oh, and then you have 0 times cosine of 0, which will be 0. That entire first term evaluates out to 0. Sine of pi over 2.
0 or 1.
Sine of 0. And so that second term will evaluate to 1. Pi over 2 squared.
Pi squared over 4.
And then divided by 2 is pi squared over 8. There's your circulation. Negative 2 over pi minus pi over 4. Right, either of those would be acceptable. Which is definitely a lot easier than trying to set that up as 3 separate line integrals. So that is Green's theorem. Questions on Green's theorem before we move on? Stokes. Let S be a piecewise, smooth, oriented surface with a boundary that is a simple closed curve with positive orientation. F is a vector field with component functions that have continuous partial derivatives on an open region containing S. Then the circulation, F dot dr, is the flux of the curl of F through the surface. Stokes' theorem writes circulation as a flux integral. Or vice versa. If you have an open surface with boundary C, and you're trying to find flux of a curl field, you can write it as a circulation. Now, how useful is that really? And generally speaking, not very useful. Right, if you're asked to find flux of a vector field, if you wanted to use Stokes theorem, you'd actually have to determine, okay, well, that vector field is curl of what? If you want to write flux of circulation. Right, generally speaking, it's just, here's a vector field, find the flux through some surface. Well, in order to use Stokes theorem in the other way to write the circulation, that vector field has to be curl of another field, right? So if you're given G, flux of G through a surface, and you want to use Stokes theorem, you need to find the vector field F that G is the curl of, because then it's circulation of that field F. So not extremely useful. Unless you happen to already know what it's the curl of. Of the three, this is my least favorite. Because then you're just left with, okay, well, am I going to do a path integral or a flux integral? Depending on the closed path, neither are fun. Notice also that for Green's theorem, our vector field was two-dimensional. Stokes' theorem would require a vector field to be three-dimensional. So if you're finding circulation of a vector field and you want to use one of the two theorems, you have to determine how many dimensions is it. Two-dimensional Green's, three-dimensional Stokes. Now, what is this? I mean, we already discussed orientation of surfaces, right? It's based on what direction is the normal vector pointer, either outward or inward. And so for surfaces, you have two orientations, an outward pointing or inward pointing. How can you determine the orientation of a surface's boundary? I'm so glad you asked. First thing to note, closed surfaces do not have boundaries. So you have an open surface. Let's say there's our open surface, right? Here's the boundary of the surface. The orientation of the boundary has to match the orientation of the surface. So to determine the orientation of your boundary, imagine yourself walking the boundary. The direction you walk is the direction such that your right hand points in the direction of the normal vector. So if this was the boundary, right, you have outward pointing normal vectors, you stick out your right arm. Which direction do you have to walk? So that's pointing outwards. In this case, counterclockwise. If they were inward pointing, then your hand would have to point inwards, so you have to be walking clockwise. That's how you determine the orientation of the boundary. Right, and vice versa, right? If you're told the orientation of the boundary, you need to know the orientation of the surface. It's the same thing. Walk the boundary, the direction your right arm is pointing is the direction of the normal vector. And just like with Green's theorem, the video has a proof of Stokes' theorem. I use that term very lightly. It's not really a full proof, it is just a special case proof. Full proof of Stokes' theorem is well beyond the scope of this course. Just like we did with Green's theorem, we're going to start by verifying Stokes' theorem for a specific field and specific surface. Or boundary, I guess, in this case. We're considering the field 2x minus y, negative yz squared, negative y squared z, and the boundary of our upper hemisphere of x squared plus y squared plus z squared equals 1. Good enough government work. And so that'd be the hemisphere. I think of the top of the globe. We're assuming outward pointing normal vectors. So there's our normal vectors. The boundary of this surface is that circle, isn't it? Now we have to decide what's the orientation. So what direction do you have to walk along that boundary so that your arms are pointing outward?
Counterclockwise.
What was it? Counterclockwise. So the positive orientation would work. That's nice. Right, so what we have to do is what we want to do is calculate both sides of Stokes' theorem and show that they're the same. Starting with circulation, we'll start with the left-hand side like we did with Green's theorem. We need to parameterize our curve, which I'll call boundary of S. So boundary of S what kind of circle is that? It's the unit circle. Center at the origin has a radius of 1. You can tell that because the sphere that we're looking at is the unit sphere. And we're just looking at the upper hemisphere of the unit sphere. More specifically, it's the unit circle on the xy plane, right?
Yeah.
That would be our parameterization. Cosine theta, sine theta, 0. And since it's circulation, we go 0 to 2 pi. So circulation around the boundary of S. F dot dr. Remember, it's the integral from 0 to 2 pi. Evaluate F along the boundary. Everywhere there's an x, you replace it with cosine theta. Y is replaced with sine theta. And z gets replaced with 0. Oh, that's really nice. Your y and z components of f will just be 0. Oh, that's sexy. That'd be the integram then, right? And then dr, r prime d theta. As such. That's what we should get, right? Negative sine of 2 theta, let's just call it that. Sine squared, a half minus a half cosine 2 theta. What's the period of sine of 2 theta? How'd you get pi halves?
period is pi.
Period of sine is not pi. That's why it is. You did it right, you used the wrong period though. Because you divided what you thought was a period by 2, right? Yeah, the period of sine is not pi. It's what? Sine and cosine are so what's the period of sine and cosine? 2 pi. They're both 2 pi periodic. Tangent is pi periodic. So the period of sine of 2 theta is what? You just told me how to do it. 2 pi divided by 2. Pi. What are we integrating over?
0.
That's 2 full periods. That's fine. That'll integrate out to 0. What's the period of cosine 2 theta? Also pi. Oh. That's fine. That also integrates out to 0. That means all we're integrating is negative 1/2. Wait a minute. Spot the mistake.
What did that happen? Negative.
Reduction identity for sine. Sine squared is 1/2 minus 1/2 cosine 2 theta. Or 1 minus cosine 2 theta all over 2. Yeah, it's not a huge mistake. It's very easily corrected. You can do the dot product.
Should have been sine squared.
What about sine squared?
2 negative 2 sine squared or something.
I should have said positive
Where?
plus sine squared.
That should be plus sine squared, not minus sine squared. That's going to change that sign there and that sign there. Luckily, that cosine 2 theta went to 0 here, so that wasn't going to affect anything. So we're actually integrating 1/2, not negative 1/2. 0 to 2 pi. Isn't that just pi? So I'll just write that up here. When you got into circulation, we got pi, which means when we find the flux of the curl field, we should also get pi. Oh, yes. All right, so let's do it. For the flux integral part of Stokes, we need curl of f. So go back to f. Remember, curl is essentially the difference of your mixed partials, your cross partials. Partial y of your z component. What is it? Negative 2yz. Partial z of your y component. The exact same thing. So your first component of the curl is 0. Partial z of the x component. What was it? Partial z of the x. 0. Partial x of the z. Oh, yes. Second component of curl is 0. Partial x of your y component.
0.
Partial y of your x component.
Negative.
Negative 1. 0 minus negative 1. That is our curl field. Oh, yes. Only way that would have been nicer is if it was 0, 0, 0. We need to parameterize the surface. What was the surface?
Unit
circle. Or the hemisphere.
Right, hemisphere of the unit sphere, right? What's the parameterization of the unit sphere?
Cosine.
What was it?
Cosine.
Yeah, this is one that you might want to remember. This is one that's used a lot. I would write down the parameterization of a sphere. Just a general sphere. And then adjust as necessary. That's the parameterization of the unit sphere. If it's a sphere, theta goes 0 to 2 pi, phi goes 0 to pi. But it's not a full sphere, is it? It's the upper hemisphere. Does theta change? Does theta get restricted if you're doing the upper hemisphere? No. What about phi?
Yeah.
What does phi become?
0
what? 0 to
pi.
0 pi would be the full sphere.
I4.
Pi over 2.
But doesn't it originally go to pi over 2?
Now, for a sphere, a whole sphere, theta is 0 to pi, phi is 0 to pi. Like, remember, what does phi measure? It's the angle of declination from the positive z-axis. Right, so it would go 0 pi over 2 would be the upper, pi over 2 to pi would be the lower.
Yeah,
Part
I
of the
thought
sphere.
it was pi over 2, that's why I said pi over 4. So you just divide by 2.
Okay, so again, we have so for a full sphere, 0 pi. We also need the normal, the outward pointing normal vector. Which was already derived. For the unit sphere, that is the outward pointing. So this is going to look hideous. Until you realize we have a very nice curl. Right, so remember when you're evaluating a flux integral, it becomes the integral over your domain of the parameterization. The integrand is your vector field evaluated along the parameterization. X becomes cosine theta sine phi, y becomes sine theta sine phi, z becomes cosine phi. Oh, but our curl is just 0, 0, 1, which means the integrand remains unchanged. Oh yeah, that's why I'm so excited for that curl. ds becomes your normal vector n dA. There's n dA.
Where does the sine phi from? With the normal vector.
When you take the cross product of the partials. Full derivation like that's in the videos. But you'll see an extra sine phi come out of it. Technically, it's a rho squared sine phi that's coming out of it. But the radius of the unit sphere is 1. Right, so again, that's one that you might want to just kind of like write down on a sheet, the parameterization of a sphere along with its normal vector. So you don't have to keep going through a derivation for it, because it is a long derivation. As you can probably see, if you take the partial with respect to theta, then the partial with respect to phi, or the parameterization, and take the cross product, it's very long, very ugly. Another reason why I was excited about this curl, the first two components are 0, which means they just cancel out in the dot product. That's nice. We're just left with what? Sine phi, cosine phi? Oh, sorry, it's not pi, it's pi over 2. That was almost a disaster. That would have been 0. Two things at once. Integrate with respect to theta. To get 2 pi, right? Replace sine phi, cosine phi. Use the double angle identity. That's a half sine of 2 phi, isn't it? So it's going to be 2 pi times a half. Integral from 0 to pi over 2. Sine of 2 phi d phi. What's the antiderivative for sine of 2 phi?
Negative cosine 2 phi.
Cosine of pi.
Negative.
Negative
1.
Negative 1. Cosine of 0.
1.
Negative 1 minus 1?
0.
I hope not.
Oh, negative 2.
Negative 2 times negative pi over 2. It's pi. They're the same. As they should be. So we're happy. If you have gotten different answers, it doesn't necessarily mean you did something wrong. It could mean you evaluated one of them wrong. Or it could mean that you can't use Stokes' theorem. Right? It means that your hypotheses weren't satisfied. Right, so you have to be aware. When can you use Stokes' theorem and when can't you? Just like with Green's theorem, you have to be aware of when you can use Green's theorem and when you can't. It's like learning L'Hopital's rule for the very first time. Now you want to do every limit using L'Hopital's rule, and you can't. When you learn these 3 theorems, there's one more theorem we're going to be learning next week. Your instinct is just to immediately use them, and you can't always use them. That circulation of 2y, 3x, negative z squared over the circle x squared plus y squared equals 9, located in the xy plane. and oriented counterclockwise when viewed from above. Say it's probably best to just calculate the circulation outright. Because generally speaking, that's easier. However, that kind of would defeat the purpose of this section. So we are going to apply Stokes theorem. Oh joy. First thing you want to check, does Stokes theorem even apply? Yes. It's circulation, so it's a closed curve. Is that curve a boundary of an open surface? It is. What does a circle of radius 3 on the xy plane serve as the boundary of? What surface?
Circle radius 3, or a sphere radius 3.
A cylinder?
Not a sphere. A hemisphere, which one?
Oh, lower hemisphere?
Lower hemisphere or upper, it doesn't matter. It actually serves the boundary of both the upper and the lower. So it doesn't matter which one you use. Oh, why don't we just use the upper? Because isn't that what we used? Yeah. Except the difference is radius is now 3 instead of 1. So we have our surface. It's oriented counterclockwise, which means the surface has outward pointing normal vectors, right? So to apply Stokes' theorem, we need the curl. What's the curl?
Is it 0 second? Zero.
Oh, yes. Curl is 0, 0, 1 again. It's almost like these problems were purposely written to be somewhat simple. Need a parameterization. Parameterization of a sphere of radius 3. We're dealing with the upper hemisphere. Theta goes 0 to 2 pi, phi goes 0 to pi over 2. Oh. And we need a normal vector. Radius squared sine of phi times which is actually just your parameterization of the unit sphere. Now, what I'm going to do is I'm actually going to factor out that 3 when I go to, well, I don't think I'm actually going to have to worry about it this time. I won't have to worry about it just because of the way the curls run, which is nice. So our circulation along our curve. I'm actually not remember what F is. What was F? 2y, 3x, negative b squared dot dr is this flux integral. Right, the flux of 0, 0, 1 across the surface S. This equals the integral over the domain of still 0, 0, 1. That's not going to change. Dotted with 9 sine of phi times this vector. dA. That's the integrand evaluated along the parameterization, dotted with your normal vector dA. 0 to 2 pi, that's 0 to pi over 2. 9 sine phi cosine phi. D theta d phi. And you shouldn't have to do any work. Factor out that 9, integral 0 to pi, integral 0 pi over 2 of sine phi, cosine phi, d theta d phi. We just did that. It's just pi, so it's 9 times pi.
9 pi.
Done. I'll say from above. Questions on Stokes theorem so far? Yes.
If the orientation was clockwise, what would be the difference in calculation?
Technically, if it's clockwise orientation, it'd be a negative orientation. Stokes theorem wouldn't apply. What you could do is multiply both sides by -1. So instead of calculating outward flux, you calculate the inward flux. Right? So that is a variation of Stokes theorem. But as Stokes theorem is written, you technically can't do it. Which is why for most cases, I'd say probably 90% of the time you're going to run across in this class, it's all, when using Stokes theorem, it'll always be a positive orientation. The theorem? There's 2 questions left. We'll finish finish those tomorrow. I do have to have the Stokes theorem homework due May 1st instead of May 2nd. Because May 2nd is reading review day, and I'm not allowed to have anything due on that day. Stupid administrative rules. Make the rules, I just follow them. So I can't have it due Friday, so I'm going to have it due Thursday instead, so you get a little less time than usual to work on. Oh well. Tomorrow, finish up Stokes theorem.